Hello and welcome back to Returd. Today we're looking at the most powerful minds on the planet, and they aren't human. I'm talking about large language models like GPT-5 and Claude 4. They can write code, draft legal contracts, and solve complex math problems. When we see this, it's almost impossible not to think. They're reasoning, they're thinking. But what if I told you that this incredible display of intellect is a grand illusion? A masterful act of imitation, fundamentally different from how you or I think. Today, we are going to deconstruct that illusion. We'll explore the difference between performing a task that requires reasoning and actually possessing a reasoning capability. Our journey will take us deep into the heart of these models. We'll start with their fundamental architecture, see how we can guide their thoughts with clever prompting, explore the new frontier of models built specifically for reasoning, uncover their surprising failures, and finally, we'll survey the state-of-the-art titans of 2025. Let's begin. So, how do these models work? It all starts with the transformer architecture. At its core, a transformer is not a logic engine. It's a supremely powerful prediction machine. Its one and only goal is to predict the next word, or more accurately, the next token, in a sequence. That's it. When you ask a model, what is 3 plus 5? It doesn't pull out a tiny calculator. It answers 8, because in the trillions of sentences it has read from the internet, the sequence 3 plus 5 equals 8 has appeared an astronomical number of times. It's not calculating, it's completing a pattern it has learned is overwhelmingly probable. It's a form of high-dimensional statistical pattern matching. The magic ingredient that makes this work so well is called the self-attention mechanism. Imagine you're reading a long story. As you read each new word, your brain doesn't give equal weight to every previous word. You instinctively pay more attention to the important ones, the subject, the verb, the key details. Self-attention does the same for the model. So when it generates the answer, the attention mechanism tells it to focus on 5, 3, and more. It then constructs a step-by-step response because it has learned from its data that this linguistic structure is the most common pattern for solving this type of problem. It's a convincing facsimile of a thought process, but it's built on linguistic patterns, not logical understanding. For a long time, what happens inside these models was a complete black box. But thanks to a field called Mechanistic Interpretability, we can now start to peek inside. Researchers at Anthropic did just this with their Claude model and found something fascinating. They asked the model, what is the capital of the state containing Dallas? Now, the model didn't just map Dallas to Austin. Internally, before generating a single word, its network showed a two-step process. First, features representing Dallas strongly activated features representing Texas. Then, and only then, did the Texas features activate the features for Austin. It's a chain of association, a learned in-head reasoning process. This internal wiring also explains how these models scale. For years, we've seen emergent abilities, sudden jumps in performance as models get bigger. This has been a huge topic, even for AI safety, because it suggests dangerous capabilities could appear out of nowhere. However, a lot of recent research suggests this might be a mirage, an illusion created by how we measure performance. Imagine you're measuring a model's ability to spell a 10-letter word correctly. Your metric is exact match. It's either 100% right or 100% wrong. The model's underlying ability to predict each letter might be improving smoothly and predictably with scale, from 95% accurate per letter to 98% to 99.9%. But your exact match score will stay at 0 until that one moment it gets every single letter right, at which point it jumps to 100. The underlying improvement was smooth, but the metric we used created the illusion of a sudden jump. This is so important. It means the model's internal circuits, like that Dallas to Texas to Austin one, are getting stronger predictably. The risk isn't necessarily a sudden, unforeseeable leap in capability, but the steady, predictable improvement of internal circuits for potentially undesirable behaviors that we aren't monitoring. Okay, so we have this powerful pattern matching engine. How do we guide it to solve complex problems? This is where the art of prompting comes in. The simplest form is called in-context learning. You just show the model a few examples of what you want, and it follows the pattern. But for multi-step problems, we need something more. This led to a breakthrough called chain of thought, or CoT prompting. The idea is simple but brilliant. Just ask the model to think step by step. This forces the model to externalize its process. It generates a series of intermediate steps before the final answer. Now, this is crucial. The generated chain isn't necessarily how the model actually thought about it. It's a way for the model to generate a rich context for itself. Each step it writes down adds new, relevant tokens that its attention mechanism can use to produce the next, more accurate step. Chain of thought is linear. But what if there are multiple ways to solve a problem? That's where the tree of thoughts, or TOT, comes in. Instead of just one path, we let the model explore multiple reasoning paths in parallel, like a detective exploring different leads. An external controller gets the LLM to generate multiple potential next steps. Then, it uses the LLM itself to evaluate which of those steps is most promising. Finally, a search algorithm, like breadth-first search, decides which path to continue exploring. It's a much more deliberate, strategic way of problem-solving. But even with a great reasoning path, the model can still make a mistake. So how can we improve robustness? One technique is self-consistency. The idea is simple. Ask the model to solve the same problem multiple times, each time generating a different reasoning path. Then, you just take a majority vote on the final answer. The intuition is that while there are many ways to be wrong, the correct answer tends to be arrived at more consistently. And for high-stakes domains, we have layered chain of thought. This is a game changer. Here, the model generates one layer of reasoning and then stops. We then use an external tool, like a calculator, a database, or an API call, to verify that step. Only if it's correct does the model proceed to the next layer. This prevents errors from cascading and grounds the reasoning in external reality. Do you see the trend here? From ICL to COT to TOT to layered COT, we are progressively adding more external structure to the model's thought process. We're building a cognitive architecture around the model to make its reasoning more deliberate and reliable. This trend leads directly to our next topic, building this architecture inside the model itself. Prompting is powerful, but it's like controlling a black box from the outside. It's also computationally expensive. Tree of Thoughts can require dozens of calls to a giant model just for one problem. The next frontier is to stop prompting for reasoning and start engineering for it. This is the birth of reasoning language models, or RLMs. An RLM isn't just a text generator. It's a system with specialized internal components for problem solving. Think of it like a blueprint. Instead of an external Python script running a search algorithm, the RLM has its own internal reasoning strategy, like Monte Carlo tree search, the same one used in AIs like AlphaGo. It has specialized sub-models trained for specific tasks. A policy model learns to generate the most promising next step. A value model learns to evaluate a current position and predict the likelihood of success. And a reward model provides the training signal, telling the other models when they've done a good job. It's a self-contained, autonomous problem-solving agent. This is the fundamental shift. We've gone from orchestrating a model with prompts to engineering a model with its own internal learned mechanisms for search, evaluation, and refinement. It's far more efficient and has a much higher ceiling for performance. But it also means we have to align its entire internal process, not just its final answer. But even with these incredible architectures, the imitation game has its limits. All current models suffer from fundamental failure modes that reveal they still lack true understanding. The most famous is hallucination, generating confident-sounding but completely false information. This happens because the model has no robust world model. It's trained on a sea of internet text filled with errors and contradictions. It learns what a plausible-sounding citation looks like, but it has no concept of whether the paper actually exists. It's just completing a linguistic pattern. Another major issue is brittleness. Their reasoning is fragile. For example, if you give a model a simple logic puzzle, its accuracy can drop by over 30% just by reordering the premises, something that would never confuse a human. This suggests it's matching a left-to-right textual pattern, not building an abstract mental model of the logic. This is confirmed when models fail at simple, novel puzzles that don't match their training data. Take the candle puzzle. You have several candles of different heights. Which one did you blow out first? Many models incorrectly say the shortest one because they associate short candle with short burning time. They fail to make the simple causal inference that the shortest remaining candle must have burned the longest. All these failures, hallucination, brittleness, and gaps in causal reasoning, point to the same root cause: the absence of a persistent, abstract world model. A human reasoner uses a mental model to understand the world. An LLM only has a model of how words relate to other words, and that is the fundamental gap between imitation and true understanding. So, with these capabilities and limitations in mind, who is leading the race in 2025? The landscape is fierce, and the top proprietary labs are all engineering reasoning directly into their models. OpenAI's GPT-5 uses a smart router. Simple queries go to a fast model. Complex problems are sent to a slower, more powerful thinking model, internalizing the trade-off between speed and depth. Anthropic's Claude 4 has an extended thinking mode that can use external tools, like a web search or a code interpreter, in the middle of its reasoning process. xAI's Grok 4 is a pure reasoning monster using massive scale and reinforcement learning to ace the absolute hardest benchmarks. Meanwhile, the open-source world is innovating at a breakneck pace. Meta's Llama 4 and Llama Nematron are highly efficient due to their mixture of experts architecture. Mistral Large 2 is a powerhouse optimized for balance and multilingual tasks, and models like DeepSeek R1 and Microsoft's Phi 4 reasoning are proving that you can achieve state-of-the-art reasoning through reinforcement learning or incredibly careful data curation, even with smaller models. The takeaway is clear. Reasoning is no longer just an emergent property. It is a designed, engineered, and productized feature. The key differentiator between these models is now the elegance and efficiency of their engineered reasoning systems. So, where does this leave us? We have built extraordinary imitation engines. The journey from a simple transformer to the engineered systems in GPT-5 is a masterclass in scaling and refining statistical pattern matching. But it is still pattern matching. The fundamental limitations of hallucination and brittleness show us that scaling this approach alone may never be enough to cross the chasm from imitation to genuine understanding. The next great leap in AI will likely come from hybrid approaches, perhaps combining the linguistic fluency of transformers with the rigorous logic of symbolic reasoning engines, or developing architectures that can build true causal models of the world. We have created a spectacular illusion of cognition. The next chapter will be about turning that illusion into a reality. Thanks for joining me on this deep dive.